There we go. All right. I think we have actual quorum here. So everybody, welcome. This is Nafees bin Zafar. He's joined Digital Domain a couple of weeks ago and has a paper, awesome, at SIGGRAPH. This is not a talk. This is a full-on paper. You're not giving the presentation? Or
I am.
You are?
Yeah. Me and my student, we're doing it together.
Oh, you're teaming it up. Awesome.
Yeah.
So this is not your presentation. Obviously, you're not going to be doing a chalk talk or a whiteboard presentation in SIGGRAPH. You've got a full-on PowerPoint, but you're going to go through the paper. You have a full hour. Take us through it, man. And if you want, I can show videos. I should be able to show videos. And
yeah, let's start with the video.
Okay. Woo. Yeah, there we go. Now I can get it. Let's see if I can show video.
All right, so I'm Nafees. If some of you guys have met me, and if you haven't met me, you may recognize my name. I used to work at DD for a long time. A lot of tools that are still in use were things I wrote back in the day. And I'm going to talk about this problem that I've been working on for most of my professional career now, right? And that's fluid simulation. And I started working on this stuff here with FSIM.
I have a quick question. Which video would you like to see first?
Let's do the Vimeo one. Let's start.
Oh, the Vimeo one. Okay.
Oh.
Yeah. No, that's fine.
Doesn't really matter.
Oops, we're gonna stop. Keep talking now.
So, all right. Well, that sets out. And so this is back in the day. We were great. We were grateful to be able to run like 100 cube fluid simulation. Slowly, certainly the appetite was always for bigger and bigger and more. Higher resolution fluid simulations, and slowly machines caught up. And machines caught up, more cores. People took different kinds of approaches to this problem in terms of parallelization and distributed computing. And this is tied into like the history of computers. They designed the first computers to try to solve early forms of these numerical problems that pop up in computational fluid dynamics. Right, so the title of the paper is a Schur complement preconditioner for scalable parallel fluid simulation. It's a kind of title you need to have in a SIGGRAPH paper, though if I had my druthers, it would be called How to Solve a Billion Voxels. Now there are ways to solve a billion voxels. There are a bunch of exotic methods, and even sometimes it's just like the brute force of implementing distributed computing algorithms. I wanted to solve it on a single machine because anybody who's profiled a fluid simulation, you look at this thing go and you're like, my cores are sitting idle most of the time. It's memory bound, and then it gets stuck in this this big matrix inversion problem, and it just sits there. And most of the typical implementations are, at least in graphics, are done with conjugate gradient, and that thing's hard to parallelize. You do all these tricks, but really, like algorithmically, you're tapering off. Your parallel scalability is tapering off after about 6 cores, even in a very fancy implementation. And we have way more cores than 6 cores now. How to take advantage of this? So I'll do a quick walkthrough of the underlying fluid simulation problem here. And you'll have seen this, especially in Chalk Talks, many times. We start with something that looks like.
Oh, yeah, you're going to need a better pen than that.
Okay. Sorry.
Then maybe try the other blue one or something. Much better. Yeah.
So pointy. So we use this particular way of writing the incompressible Navier-Stokes equation. And ready.
Nafees?
Yeah.
Can you, or anyone, someone turn up the light or turn on the light? Kind of hard to see.
Unfortunately, not right away, but I'll be right back. Keep going. We'll see if I can do the light.
Okay. Well, this is some simple parts that I'm going through right now. But what I'm writing is just a fancy way of saying F equals ma. This first equation says how stuff is moving around, and then there's this totally sweet thing called the divergence constraint. But basically what this says is, in these incompressible fluid simulations, you can't create or destroy mass. And this scheme is called Torrance projection method. This is the only way to discretize and solve these Navier-Stokes problems. But this is a good one. This is particularly a good one for computer graphics, and it's standard in our world. The nasty thing, well, this is saying F equals ma, great. The problem we're interested in is, like, you move stuff around, you move your fluid around, and they've got to enforce this divergence constraint, and that takes this form, which effectively says that whatever these pressures are that are in the system, they have to be such that this divergence constraint is enforced, meaning, like, the pressures just are required to be such that all the inflows and outflows match up and balance up to 0. And we solve this here, really with these iterative. It's an implicit formulation, and we use iterative methods. This is where precondition, conjugate gradient come in. This is where methods like multigrid come in. And if you read the literature on numerical algorithms, they talk about the big O's of these problems, right? And I don't know how the one for PCG is derived, but it's this. Its big O is and most of the time you see algorithms that are n cubed or n log n or something. I've never seen one that's n to the 1.5. But there you go. It's not really that nice. And it's really hard to bust it up so you can effectively parallelize it. And the way you implement these things, the bigger and bigger these systems get, the more voxels you have in your simulation. PCG starts taking more and more memory, and it just the convergence degrades. Yeah, so PCG is kind of you can make single processors faster, and that's kind of the only way to make this problem go any faster. Multigrid gives you a better algorithmic complexity, but multigrid, the very simplest multigrid is very simple, and it's pretty easy to implement. But for our class of problems, where we often have, like, there may be a little fluid here, maybe there's some fluid here, and then there's like a very thin piece of boundary, right? And there's more fluid here. And in the multigrid scheme, you change resolutions. And you can imagine, if you go to a lower resolution, at some point, this obstacle is just going to disappear. And there are modifications to multi-grid to deal with that. And it starts to make the thing more and more complicated. And yeah, so people have done it. It works. All right, so we'll hold that thought. And we won't really come back to it. But that's not the only way to solve these class problems. When I was at DreamWorks, in between my DB years, I worked with a guy named Ron Henderson. And Ron's a super smart guy, fantastic mathematician. He got his PhD in mechanical engineering at Princeton, and then was in applied math at Caltech. And he'd worked on these class of methods. Well, a very particular one called the fast Poisson solver. The fast Poisson solver uses fast Fourier transform to solve these problems. And I'll tell you the punchline first, which is the FFTs, big O, is,
oh, Jesus.
right? I want to use that thing. So how do we do that? Well, let's first look at the fast Poisson solver. What do we have here? We're solving this problem. This is our P is let's just say well, ready, and we're just going to call this thing F. Okay, it's 0, but we'll just let's make it generic. So the way to solve this problem is you say, all right, let's start. You know, these P's and these F's, they're just signals, right? Let's do a compute the FFT of F. So what does that look like? So FFT of F looks like this. And okay. So that's I as in square root of -1, imaginary number. And I'm using E because typically, you know, if you remember something about FFTs, you probably remember something about sines and cosines. I'm using some shorthand because we can run it through Euler's equation, which relates exponentials to trig functions. It's super elegant and beautiful. For our purposes, it does help me illustrate a point better than with sines and cosines. Okay, so then we can do that for F, right? So these are the Fourier coefficients, wave numbers, which term we're talking about. And great, that's very standard. This is why FFTs are cool. This lets you represent the signal here as a sum of waves of various wavelengths. We can do that. We can take the FFT of P, not this Laplacian operator, but just P itself, which looks similar, right? Great. Now, one cool thing about E is the derivative of itself. So computing the Laplacian of this thing is super cool. Is going to be so when you compute, like, what's the derivative of e to the nx? It's n e to the nx. Well, and there's I here. So that's why the negative sign shows up, because we're computing second derivative of this thing. 2 i's come down, that turns into -1. 2 n's come down, that's your n squared.
Yeah, capitalize that.
Yeah. So that's cool. And look, this thing is still a very simple looking sum of trig waves, right? Awesome, great. But we don't know what P is. We want to figure that out. Let's write this again now with now in frequency space. So right, the exponentials cancel out. Things go away. And we're left with whatever these Fourier coefficients are for P are going to be there's no these aren't symbolic. These are floats, right? That's just an arithmetic computation. So once you have these Fourier coefficients for P, you reconstruct, you reverse the FFT, you get your signal back in your spatial domain, and you're done. This thing has solved this problem. And way faster than anything else. But you can't just run FFTs on all kinds of signals. Again, our problems are boundaries, right? You jam some irregular boundary into your fluid domain, it's going to blow up. FFTs really want these regular, like this scheme is only working out because if you imagine the A matrix here has like constant coefficients. It doesn't like if you look at any particular row, they all have like it's 4 on the diagonal or for 2D or 6 on the diagonal for 3D. That's why that scheme works out. So it really needs these regular domains. If you jam boundaries in there, it's not going to work. The coefficients are no longer constant, and this thing you just can't do any of that. Well, poop. Now, I mentioned Ron Henderson because he said, you know what? Gas simulations are pretty forgiving. That you can't ignore boundaries, but you can do something else, which is you can go in and you can run an iteration of this solve, and you go back in to these boundary regions, and so you run the solve as if there are no boundaries in there. It's just that these areas have velocities, right? And so Ron was like, you know, this thing is so fast, I can run it multiple times, constantly resetting the velocities after each iteration. And this will be cool. This will work out. This will be pretty okay for gases. And turned out he's totally right. You can't tell the difference. If you run a big gas simulation, a 512 cube gas sim, and with internal boundaries and whatnot, no problem. These boundaries with the velocity setting condition just makes, like, you can use this FFT just to run a few iterations of it. Certainly not up to that much because you just have to run like 5 or 10 iterations. Cool. Well, I saw him do this and I was like, man, we can't use this for liquids. And then a guy who also worked with us named David Hill, and had worked with Ron before at Caltech, said, you know, in the mid-90s, Ron wrote this paper. You should go look at that paper. And so I did, and it was like a hardcore CFD paper, right? And it's done in 2D, and he's tracking like vortex shedding or something. I can't really remember what the content was. But he used this method, called the Schur complement method. And he used it to take a domain and he's using it as a parallelization scheme. So he goes like, all right, well, let's split this thing up. Let's deal with each of these sections of fluid differently. And he's not solving for internal boundaries or anything like that. But it was intriguing because I made me learn about this.
We've got a life-size guest. Make sure all the life-size people mute their microphones. Otherwise, I'm just going to turn you down. And keep on going. I think it's MB. Yeah, Teal, can you mute? I think that's you. Or log out. I mean, that's it.
Okay.
Dude, all right.
So I'm still doing a whole bunch of setup, and we're, oh my god, halfway through.
Yeah, but it's good setup.
Why? So this is how I find out about this method. I don't really know very much about it, and he doesn't seem to have used this FFT thing at all, and it's solving a different class of problems. But Dave says, well, I think there may be a way in there to incorporate FFTs. And so I read a little bit more about this method. And this is a good point for us to get into what this method is. The Schur complement method was cooked up. Well, the Schur complement decomposition was cooked up in the 1800s by this guy named Schur. And I think he died a pauper. As happens with brilliant people often. Certainly in the 1800s it did. And so he says, you know, if you've got this domain, take a domain. One way to decompose it is to take a couple of, take this into interior regions. And, you know, let's call this region A1. This is A2. And then there's this interstitial boundary region. So you can take your full domain and you can break it down. I'm going to use gamma here. And these are in our world, these are voxels, right? We're using finite differences. These are all voxels that are so on. Your A matrix is going to look like this. You can decompose your system to look like 1, 0, gamma 0, A2. 1, 2, where the coefficients that just pertain to this region can get plopped in over here. These goes over here. The setup for all this interstitial region goes in. They're all block diagonal. Goes into this last corner block, and then these other matrices are controlling the interaction between like A1 with the boundary region and A2 with the boundary region.
You put an equal sign there, but you've got zeros. They're not equal, right?
They are equal.
The same size?
Yes.
The same everything? Okay.
The fill is different, right?
Okay.
The pattern's totally something else. But this is the Schur complement decomposition. It says you can rewrite your A to be like that. Well, this is the magic.
Okay.
Okay.
So A is not a completely dense matrix. It is
A is our usual A.
Okay, A is
right?
the Laplacian.
Yeah, A is the Laplacian.
Okay.
It's that if you decompose it like this, you can rewrite it like so. Okay. And you know, it's not quite a free lunch. This construction has a different, the condition number on it's different, so it'll converge different at a different rate. So it's not perfect. It's not totally free. It's not like just for purpose of a numerical implementation, there's an impact. But oh, so that gives us A, and then for the x that we're trying to solve, x1, x2, x gamma, and similarly 1, 2. All right. Okay, so I'm going to need some more space. I'm going to erase these here. I should have written them down here, but all right, I'll do it really quick.
So you've just broken up X into 3 different sections.
That just correspond to the pressure values we're computing for that region, that region, and that region.
Got it.
And our B is
and there's been some serious reordering of the indices, right?
There are, but internal to these regions, it's as you would do them.
Oh, really?
Yeah,
okay, cool.
Just pick a corner, just start counting up, and just pretend like, so when you're computing the indices for this, pretend like these are boundaries that you're not indexing.
Got it.
And so on. All right. So if we write now our AX equals B, what does that end up looking like? So let's take our first row, we'll multiply it with this, with the X, and we have, so A, say, I'm going to use the subscript K to indicate these numbers. And I'm just writing it generally for these first two rows. X of K. Gamma. Sub. Gamma. Okay, all I've done here is just multiply that to that, and then so just explicitly write out the AX equals B for the first 2 rows. And so if we rearrange it to show the thing we're solving, it's getting A. Okay, and this is just straightforward algebra, right? Gamma. So I just move that thing over there, and there's the inverse of that on the other side. This is what we're trying to solve for, right? And this is for K in rows 1 and 2. And we've got this final row, which is different. So 1. So again, that. Well, some things from up here start showing up here, right? So, for example, this thing, are results of this first part. So if we substitute all of that in, this is the most fun I've ever had doing linear algebra, by the way. Because I'm going with one particular derivation that gets me to the point a little bit quicker. There's another one that gives you more intuition. That one takes like 3 whiteboards. It's so fun. Because you just, everything that you've ever learned, you start having to use. All right. So it's plug and chug, right? So I'm taking these XK expressions, so these things, and lumping them down here, which gets me I'm just going to write everything out. Okay. 1 inverse. Gamma. I'm going to erase this.
Yeah, that's fine.
Yeah. Just remember, FFT, super easy. Now you know why. All right. Two inverse. Any questions, by the way? I'm just writing down some expansion here. So I haven't really done any work here. I'm just expanding these things out. And if we collect these terms, we end up with, what do we got here? So there are some unknowns. The big unknown here is that, right? These are our unknowns. And so we're going to multiply everything through, parcel it all up. Things that don't depend on this end up going over the other side and subtracting from the b vector, and everything else remains, which turns into gamma. You can imagine how the indexing hell that is involved in implementing these methods.
Because you've broken it up into just 3 different, or 2 subdomains in the A gamma. You
That's
could have
right.
as many as you wanted, right?
Yeah.
Uh-huh.
So here's this part. Gamma. Okay. This sucker here is, if you read the literature, they often use this S term. This is the Schur complement matrix.
Oh.
Okay. And so to write it slightly more compactly, this is too low.
No, you can go low.
All right.
Yeah, everybody can see you.
Okay. So, well, S gamma. And when I got to this point, by the way, this is circa 2000, I want to say 13, maybe early 2013. I understand Ron's paper. I go back. And by the way, in Ron's paper, it's like 2 sentences where he says, and I used the Schur complement method, and I used a direct LU decomposition. And that's it. There's really no details because that wasn't the point of his paper. He was talking about the physics. And so I understood what those 2 sentences meant by going back through, reading a bunch of stuff, working out all of this. And I got it. I understood why my friend David Hill said, go look at Ron's paper. And that's because the computations of these A inverses, right, are decoupled from everything else that's going on. And they're decoupled from each other. And I can go, one great thing is, this is why Ron was using this initially, I can go and solve these things in parallel, right? So right away, I've got this parallelization in this problem that I didn't have before. And then the real insight that I think David was trying to lead me towards came up, which is these are independent systems. I can solve them independently. I can use totally different solvers to use them. I don't have to use the same numerical method. I don't have to use PCG for the Schur complement system and the internal ones, or multigrid for everything. It's totally decoupled, right? I can use FFTs. So if I have a big liquid simulation, and in interior regions of the simulation, there are lots of subregions that are entirely fluid, I can use the FFT in those regions. Right? That was the big aha. Oh, there's a payoff here. Right? There's a way to get much faster solution to the pressure projection than PCG was going to give me, not only because I could parallelize, but also because in regions, for particular kinds of flow, I could get an algorithmic speedup.
But you have to solve for X gamma before you can solve for the A1s and A2s.
You can, well, since they're decoupled, you can solve these things, and where the other, so where the A gamma acts as a Dirichlet boundary condition, and then you can solve for A gamma, and then you ping pong this. Right? So, and that's numerically going to converge. That's so really the problem now.
Oh wait, why do you have to ping pong? Because the X1 and X2 are dependent on X gamma, but X gamma isn't dependent on X1 and X2. Where'd they go?
So the pressures are going to propagate back.
Yeah. So I need to, yeah.
You need to go forward and backward.
Right.
Yeah, you need to propagate that information. But what these systems that we're talking about are considerably smaller than our original big A. So they, it's not like I've doubled my work where I now have to compute for the inverse of these regions and then solve the whole thing. I'm solving much smaller systems. But solving this thing is the key. And this is a nasty matrix. And then I read a little bit more. I was like, oh, there isn't, again, a free lunch here. Trying to solve this problem is almost as bad as solving. So if you imagine, let's say I had instantaneously fast ways of computing these things. Well, the inverse of a sparse matrix is not sparse. right? These matrices start to become, while much smaller, still pretty big, and now dense. And I'm pretty much back to n cubed for this part, which blows anything else I've got, right? And of course, I wasn't the first one to realize this. People have been trying to use this domain decomposition method for decades, and well, they've come up with ways of dealing with it, and that's by saying, that's by doing what we usually do when we are handed a nasty matrix and we have to use an iterative method, which is precondition it. Let's come up with a preconditioner that makes this go fast, where I don't have to do nasty stuff and form a big dense matrix and then try to invert it. Let's see. So, but this is, in my story, I'm still back in 2013. I've gotten to this point that I'm stuck because I'm not a good enough numerical, numerical linear algebra guy to find something better than what had already been developed. So I had to shelve it. And a few years later, I went to China. I became a manager. I didn't have time to work on deep problems. And in 2015 summer, I had this intern. She was a new master's student in one of the local universities. Her undergrad was in math. She had ended up in a computer science department working in computer graphics. And my impression was that she wasn't really finding a nice home in the group she was in, because there were a bunch of computer science people who know lots about algorithms and code and C++ and OpenGL. And all she knows is a bunch of math. So she did an internship with me, and I had her work on, I can't even remember what, point cloud processing or something. And in the stuff she did, I was like, wow, the way this woman thinks is really kind of unique and rare. And I think she can solve this problem. So I talked her into coming back after the summer and said, here, come keep working here. And this is the thing I want you to work on. Figure out how to make your complement system go faster. At least implement. This is a master student. If she just gets an implementation, and even if it's no faster, that's probably enough for her thesis. So she starts working on this. And she's the kind of person who can just delve into deep linear algebra and just try a billion different things and has all these great ideas. And she spends months doing this and discovered what everybody else in this field had discovered, which is it's really hard to precondition this thing. All right, 10 minutes. All right, so real quickly, what's precondition? We've got this problem. X equals B. A is hard to invert. And so there's this idea that what if there was this other matrix, M, and we multiply both sides with M. And M is kind of, M inverse, is kind of sort of close to A inverse, right? So if you can come up with such a matrix, well, in the simple case, just for illustration, if M was exactly A inverse, then you'd see how this solves the problem, because this becomes identity, and then you have A inverse over there. But now we've not solved the problem any faster. And if M is identity, then you've done nothing. But if M is kind of close to A inverse and has a much better condition number, then you've gained something. You've gained your speed up. Let's see. So there's this concept of condition number, and numerical methods, this pops up all the time. And what a condition number really says is that how much does X change when I change B? Right? What's that scaling factor of like how? So a low condition number means like if you change B, X doesn't change a whole lot, and that's nice. That's what you want. But if you change B a little bit and X really like starts changing wildly, that's bad. That's going to the impact of that is that this convergence is going to take longer and longer and longer. So the thing we're trying to figure out with this system is an S inverse that's much cheaper than actually taking S inverse. And that's what my student, Chu Jie, is working on, right? And after a while, she gets this super cool insight. First of all, in 2D, I'll show a hint of what it means, but it really starts paying off in 3D. First of all, she says, you know, I've got these few voxels that are in the corners between regions. So that's just in 2D. And they're not actually connected to the fluid regions, right? Because I'm just using, so if you're just using like a 5-point stencil in 2 dimensions, you're connected, you're the only other voxels you're connected to are also in this like boundary region. They're not actually connected to these internal subdomains. Okay, and in 3D, you extend it out. You don't just get single voxels that are like that. You get whole like wires, and the term there is like wire basket. If you imagine taking a big fluid simulation, tiling it up into a bunch of like rectangular regions, eroding it by one voxel, and what you're left with, and you look at like the voxel that don't actually touch any of the interior subdomains, that's this big wireframe, right? So she goes, well, those things aren't connected to anything. So I can actually take this and dice it up a little bit more. I can dice it up into the regions that actually interact with my subdomains, and yet another subdomain that doesn't. And it turns out that itself makes an improvement on the convergence of this problem. And she takes that thought one level further, which is to say, I'm trying to construct this preconditioner. I'm going to use the Schur complement decomposition on the preconditioner to compute the preconditioner. Nice. And that's kind of the big leap that, and this is the thing, you know, this is the kind of thinking that I don't think I would have gotten to, and she obviously did. Let's see. So where am I now? What do I want to show you next? The paper then. So there's one other super clever insight, and I take a little bit of credit for this one. When she was working on this early on, and she was kind of like still kind of stuck in the weeds, I told her, you know what? This is you're just stabbing at ideas here. Take a structured approach, write unit tests. Okay, and I forced her to work on some fairly tedious, boring unit tests, but she did, including ones in 2D. And so as she's attacking this problem further and further, one bit of insight she says is, I'm trying to compute this preconditioner, which doesn't have to be exactly like A inverse. It just has to be kind of like it. And one of the things that she does is, let's see if I can try to draw this in 3D. It's a little bit difficult. So there's what I'm drawing here is, so this thing that I've drawn is this one of these layers of the wire basket I mentioned. And this wire basket, these voxels in the middle of this wire basket really don't have anything to do with anything else. And so, you know, and another thing is that for the preconditioner, you also have these like big flat regions that are the these faces that are sitting between the 3D subdomains. So for the purpose of the preconditioner, let's take those flat regions and treat them as 2D problems, because the 2D problem has totally different convergence properties that she knows because she ran these numerical unit tests on 2D problems, right? You can go and compute. One of the tests was like, it's like, don't tell me that something has, you think something has less convergence, like compute it. Tell me, show me that it has less convergence. So she's got this technique, a very rough, approximate, heuristic-driven, but not numerical nonsense technique of saying, all right, well, I can utilize this 2D approximation to this effectively in these cases 1D approximations to solving the Schur complement preconditioner on the subdomains themselves. And that's, you know, there's a lot of details in the paper about how the preconditioner matrix itself is structured. And when you go to implement it, you have to pay attention to that. But the idea there is when you're computing the preconditioner for the Schur complement system itself, take the Schur complement regions, so these boundary regions, right, and construct those regions themselves as Schur complement problems. And where those regions touch the original fluid subdomains, like use the Neumann boundary condition against those other fluid subdomains. So you're like that's not physically quite right. But again, you know, are preconditioners bound to being physically sound? They're not. They're just bound. You're just trying to reduce the complexity of this problem. You're just trying to make this thing go faster. And for the purposes of fluid simulation, at least this particular physics problem, this works out okay. This gives you a preconditioner for the Schur complement system that improves convergence, that makes this thing go faster. How am I doing here? Oh, got 2 minutes left. I didn't get to go into as much detail as I wanted, but I want to give you a couple of parting thoughts here. And we didn't play the movies.
We did not play the movies, but we can as we're leaving.
Okay. So part of this is like when you try to compute a simulation that's this big, you know, if you're just trying to compute this AX equals B problem, that's fine. But now we've run into sims that are so big that your standard pick-flip method, it just takes up too much memory, and just transferring between particles and grids and back takes too much time because there are too many particles. So there was a paper, I think last year, called narrowband flip. So we ended up, for running anything that was like bigger than 512 cube, we had to use narrowband flip, and you know, Houdini doesn't support that, which is too bad. But the NB flip authors had released their code, so we ended up using that. And you kind of have to, right? Once you've gone this big, there are other factors that are coming into play. So this method is great for multi-core systems, but if you wanted to do this distributed, there are problems. You have to exchange large pieces of data, and not just like boundary data. So that sucks. Tuning the solver was another cool thing. So it turns out if you can make these subdomains small enough, let's say 8 cubed, well, that's a 512 by 512 system. You can use a direct solver. It's a compute-intensive operation, but on modern hardware. That's cool. And one of the things you can do, so this starts to get away from my original motivation of wanting to use FFT, is if you've got lots of these regions inside the fluid that are entirely fluid, so the constant coefficient regions, right? We wanted to use FFT, but we could also make them small and use LU decomposition. And LU decomposition, it's only dependent on the structure, right? It doesn't, so you can solve it once, you can cache it for every region that's the same and just reuse it. You're backstopping it over and over, and that is faster than FFTs. But it's possible that one big FFT FFT of a bigger region is faster than lots of little LED compositions. So it's very flow dependent, fortunately, or fortunately. This is the area for new research, if somebody wants to go figure this out. And then finally, I'm not sure that anybody's really interested in graphics in making faster solvers anymore, because I feel like 3 years ago at SIGGRAPH, people are very excited about this paper. And this year it'll land with a thud because people just care about machine learning based approaches. That's not a bad thing. But perhaps the CFD community would be more interested in something like this at this point. You are solving this problem. So this is a sim that was actually done by an effects artist at Oriental DreamWorks who now works at DD Vancouver, P.T. Wang. Really, really great guy, and a great artist. It's very helpful. So there's that, and it's just a big, long reverse simulation.
So I brought this one up first because I have a question about this. How effective is the Schur complement method on something like this, where you've got a long path of very thin, not big blobs of water? And then we'll ignore that for just a moment, and then we'll.
Yeah, I think this one was about 3 times faster.
Still, yeah. Wow.
Yeah, but
all right.
It's just that there's just the pressure projection, right? And there's still the rest of the fluid simulation to deal with.
Yep. And now we're going to have to stop. There is another video, but you'll have to ask Nafees for that one.
Yeah, and if you're going to SIGGRAPH Thursday morning.
Thursday morning. Thank you so much. This was brilliant. Thanks, Nafees. Bye.